ask about here had to do with the requirement of solving a fairly simple question, but it requires a graphical solution. Let me see where my solution to that is here. It appears that I may have forgot to bring my copy in here, but I remember it pretty well anyway. Well, what particular problem or aspect about you want me to go through what the answers are? I think I did. Thought I had that with me, but I apparently let me look once more. Oh, I have my solution here. All right. There, as I said, the problem, of course, has to do with graphical integration. To solve the expression, because we don't have any method algebraically representing the equilibrium data for ethyl alcohol and water over the range of concentrations that are involved. So in other words, we're obliged to solve for the ratio of the quantities of the liquid at two times, one of which would be the start and one of which would be the end, in terms of so in other words, it's solving this thing graphically. And so if we can plot x against the function 1 over y minus x. And I think between plotting it up to about 20% here is as far as we needed to go, that you got a curve that was some shape like so. If you plot it all the way out to 100%, it'd go back up like that. But and so we want to know what this x1 was 20% and x2 was 1% by weight. And I remind you once more that since this problem does not require any assumptions of equal molal heats of vaporization or equal molal overflow, that you can work on a weight percent basis just as well as you can on a mole percent basis. And so that was the basis by which the problem was stated. This is weight percent. And so what you do when you integrate graphically between two values here is simply we're adding up the sum of the little differential quantities of x multiplied by the vertical dimension, which is 1 over y minus x. So that multiplied by that is what we want to know, but we want to sum it up, so that's what integral is for, is a summation. And so the solution to that then is measuring the effective area under this curve from 1% out to 20, or technically from 20% back to 1 if we want to keep our logarithms positive numbers. And so I mentioned before there are three or four different ways of doing that. The most direct way is count squares on a paper. Probably this may not be the most precise, or maybe a little more tedious than others, but it's probably the most direct approach. Another way that can be done is to instead of adding up dx by integrals, you can approximate that by adding up more discrete segments, such as delta x, taking it for each percent or maybe each % and adding them up. The product of a certain dx, like well, you might take 1 times whatever this height is, and then at 1%, and then 2%, and 3%, and you add it all up out to 20, and that'll give you approximately the integral by by taking a summation of delta x times 1 over y minus x at let's say 1% intervals. This method is perfectly satisfactory if you take into account, of course, that here, if you at 1%, if this represents from 0.5% up to 1.5%, well, then of course you have to add only half of it, because this part here is outside the area. But when you multiply at the value of 1 over y minus x at a value of x equal to 2, well, then the whole thing is carried out, and so forth, until you get over here to the value of 1 over y minus x at 20%. If you're multiplying by 1% intervals, why, of course, the one outside here has to be dropped off. So you'd take a half of that, you see. So that's the second way of doing it.
In that method, though, you still get those little triangles up on top that are extra, right?
Well, of course, when you do a system like this, like when you do this, and let's say count here, you're actually counting this much, which is too much. But maybe the next time when you add it up, for 2%, let's say if this is 2% here, in effect you're adding up this here, and so you have a compensation most of the time here. But at this 1% here, if you want to be precise, why you actually there's a little bit of error here because of the shape of the curves. So you can make an adjustment for that. Let me see. I gotta. I'm sure you can't see this very well. In fact, the copy is not too good of my original plot using this method. But these little shaded areas here you see are the parts that are really in error, or are the error. And only if they equally compensate is the way to do that here. For example, here this is when I take the first 0.5% here. Well, I got this much above here, which is included by the simplification method, but it's not really under the curve. But when I take the next step here, I'm neglecting this much under the curve, but adding on that much. So anyway, you see, actually then I made an estimate of this error and subtracted that from my total. And when I did that, I got almost precisely what I got by other methods. So in other words, the methods for graphical integration count squares, estimate delta x times 1 over y minus x at chosen intervals. Of x. Third, you can use a plane emitter. I forgot to trace mine down that's missing from office to show you what it looks like, but maybe I'll try to get that yet. And fourthly, you can cut out and weigh the paper on analytical balance, or a reasonably accurate balance. And maybe there are other methods, but that's what I've used. I've solved it those 4 ways, essentially get the same answer. Question?
Yes, in choosing your increment of x, so just a practical suggestion. What you want to do is select an increment of x that varies in such a manner that the product of the increment of x that you selected times 1 over y minus x is about a constant. Otherwise, you're wasting your time when the thing begins to flatten out.
Well, that's true. After it flattens out, you can simplify it somewhat. You can make a little estimate here and multiply maybe from 10 to 20% all at once.
You're not going to improve your accuracy.
No, that's true.
You must decide that
That's true.
vary the area that you found very, very much.
That's right. Yes, from here, from roughly 10% out, you could sort of take the kind of by inspection, take the average 1 over y minus x, multiply them by whole 10 units at once. Be just as good a solution. Well, of course, these are the ways of doing it. Now, the question, of course, is that a lot of students get bogged down in is converting what you actually measure on a graph paper to the units that numerically represent this interval function that you're after. For example, of course, if you do it this way, this method here, you're actually using the correct units. So that the summation of this is the estimated interval summation. If you cut out the paper and weigh, you get the ratio of the amount, you get so many grams here. Well, that doesn't mean anything unless you relate it to something. So you have to relate it to something such as the product of a known area. You can take some rectangle here. It can either be the top here or it can be any unit here, which you can count you can either count the weight or count the squares and relate it to the product of the distance here to the vertical distance. And so the fraction of that under the square in relation to some rectangular quantity which you can define in terms of these units would be then representing the fraction of these units under the curve. Well, I glanced at a few of these. Mr. Aliotto did the grading. If you still don't understand this, maybe you better work it out again or work out a similar situation. Is that enough discussion about this problem? Or any of the other 3 problems? All right. Now, are there any questions about how to proceed on the requirements? I guess I asked for you to hand them in tomorrow, didn't I, on the fuselage separation problem? Or problems.
I don't understand number 3.
Well, in other words, let's see, that problem set, labeled set number 8, gave you a situation, then asked for the relative quantity of the oil layer separated at 25 degrees.
You mean, is number 3 versus the amount that's in the water layer?
And then number 2, what's the concentration of fusel oil in each of the phases? That's read off the graph. Part 3 was percentage removal of fusel oil in the separated oil phase. Well, how are you going to get it? By you're using the part of the answers from parts 1 and 2, because from part 1 you get the quantity of the oil layer separated. You get it by graphical ratio of the ends of the length of the tie lines. And you read off the concentration off the graph. So you have some sort of a curve here. I don't remember exactly how it looks like. And then you have, so you'll have some initial concentration here of your mixture represented here. And then by water dilution, you tend to approach, I didn't draw this quite right, but I don't know where it'd be. But anyway, you tend to approach on a straight line the water apex of the triangle. And after we have added the amount of water that is stated here, you will end up at some place down here, I imagine, somewhere on this line. And it probably doesn't coincide with one of the tie lines that are drawn on the graph, but if it isn't, you draw one in there by estimation, as near. These are not quite parallel, but by eye you can draw it in a reasonable, proper curve from looking at the others. And of course then, if I want to use letters here like A, B, and C, the length, graphical length of this distance, AB over AC, is the fraction of the oil phase. And similarly, the rest of it would be the other length of that, or in other words, BC over AC is a fraction of the water phase. Well, from the stated requirements and the solution here to the parts 1, you can get the grams of the oil phase produced. Because let's say you're going to take 100 grams of the original mixture as a basis. That'd be the recommended basis, or 100 pounds. And you add, what is it, 2 parts of water? So in other words, you added 200 grams of water. So you got a total of 300 grams then in your dilute mixture. And so if you know what the fraction then is, well, of that total, it'd be just that fraction of the mass that represents the mass of that phase. Then you just read off here what the concentration of fusel oil is in there. So the concentration times the mass, of course, will give you the amount. And that fraction of the amount taken in the original mixture would be the percent recovery. And of course, this last question, of course, would be how much water did it take to come down to the point where you've just intersected the curve? The amount of water, the part D, or part 4, what is the minimum quantity of water to be added to just initiate phase separation? Well, this curve, of course, represents the solubility curve, so when you just add enough water to actually touch the curve, that would be what would initiate separation, wouldn't it? Or in other words, you might say, could have asked the question otherwise, what is the minimum quantity of water that would be needed to produce 2 phases? Same question, same answer, same meaning. Incidentally, now that then leads directly into, unless some other question about the problem. Yes?
Yeah. Up there, is that the fraction of each of those phases that fusel oil is, or is that the fraction each phase is of both of them together?
I mean, this ratio I just wrote here?
Fraction of oil phase, is that the fraction of both solutions?
It's fraction of the oil phase, but it has a certain composition given by this point here, which includes isoamyl alcohol, some ethyl alcohol, and some water. each phase of them has all three components in it. This is not drawn to scale, but it's roughly the way it is. I don't know what it'd be, maybe it'd be 80%, something like that order of magnitude of isoamyl alcohol in this phase. Over here is the water phase. We would call it that because it's mostly water. You see, it's over here near water. Maybe it's 90% water, something like that. This is like we've discussed before when we're talking about immiscible mixtures. When you have two phases present, why you have, even if you're considering the binary system, you'd have, when you have two phases present, let's say like water and isoamyl alcohol, you'll have a lighter phase floating on top, but that'll have some water dissolved in it, but it'll be mostly isoamyl alcohol. The bottom phase would be mostly water, but there'll be a little isoamyl alcohol dissolved in that. Here, where it's being modified somewhat by the ethyl alcohol, which acts as a solvent for both, so it increases the solubility, as that curve indicates. Well, anyway, maybe you'll never have to work with this thing, but I think it's a good mental exercise to understand these. And so, as I started to say then, this leads into the point I wanted to make about the handout I gave you here. You recall that I think the previous period I gave you an initial sheet which showed it was actually figure 2 out of this paper I referred to, and showed the solubility curves at 3 different temperatures, and then another figure which showed the tie lines in here, or in other words, it's simply a copy of the graph I handed out to you to use for solving the problem. But it has 3 examples here of A, B, and C initial mixtures, and and so following up on that was the next 2 pages out of this kind of a montage I made out of the data of this particular paper. So a few of them came out, some of them came out blue, so don't worry about that. And the one that, what I handed out today would be page 2 and 3 to go with that. And referring to figures 4, 5, and 6 represents a graph based on using these mixtures represented by A, B, and C on this figure 3 of the previous handout. And so by using a graphical solution like the one example we worked here for this problem, where you can determine at various amounts of water added for such factors as the concentration of isoamyl alcohol in the oil phase, which is one of the questions asked in your problem set. You can calculate the percentage of isoamyl alcohol removed in the oil phase, which is also, I guess, what we actually need to do. And we can also read off graphically the percent of ethanol in the oil phase, the percent of ethanol in the wastewater, and so forth. And so I've done that for these hypothetical cases and plotted curves here. The purpose of this, at the time I did it, was partly to demonstrate to people that the amount of water added is very significant. The amount is important in getting a successful separation and practice in distillation operations. So you can see there, of course, that until you get a certain amount of distance out on the axis here, which represents the dilution ratio, you still have only one phase. And then when you phase separation is initiated, well, then you can plot these functions in terms of amount of water added. And so if you want to look at the curve which says the percent of the isoamyl alcohol removed in the oil phase, that means the percent of the initial amount fed to the decanter. You see in figures 4 and 5 there that it goes through a maximum. In the case of figure 4, for mixture A, at about 2.5 parts of water per part of low oils, or fusel oil fraction. In the next case, it is only about 1%, or about 1 to 1 water ratio. And in the next case, which is really rather impractical because it's so high in fusel oil that you wouldn't normally ever have that situation represented by C, well, it only takes a very little amount of water to initiate separation, and the percent removed in the oil phase is that what you'd obtain almost at the minimum amount of separation. So part of that led into the discussions and recommendations having to do here. I won't go through all these, but a few principles I enumerated here in a proper successful fusel oil decanter are, I might mention a few of them. When you start up with and let me also back up to say that what we're talking about here really has application only when you're operating a column to produce high-proof spirits. Because if you're distilling at a low-proof spirit like beverage brandy strength, you will never get sufficient fusel oil to build up to cause separation by simple water dilution. So we're talking about the situations that would pertain when you have such conditions such as illustrated by this table that I handed out also last time, where you have high concentrations of fusel oil accumulating on the plates. And the reason it's accumulating on the plates down low in the column is that the proof of distillation is so high that the fusel oil components are almost negligibly volatile. It's very much less volatile than ethyl alcohol, so they're forced down the column. And you can see here they build up to 25 or more percent. So in other words, if you're starting up a distilling unit that's been washed out and cleaned up or first day of the season, there's no point in turning on the fusel oil decanter for a day or two, maybe 2 days, because there won't be enough accumulated to give you any separation. I think I suggest here 24 to 48 hours. This, of course, is sort of a rough conclusion because it depends on the actual holdup of the liquid in the column, how many trays, how much liquid is held up on a tray, and what strength you really try to have before you start it up. Well, one of the most common errors is drawing it off at the wrong level, at a tray where there isn't any. So that's one of the main problems in operation, is to operate the column in such a way that the higher alcohols are in the region where you're going to draw it off. So I mentioned, as we have already before, that the tray that's about closest to indicating a strength of 130 proof, which is around about 185 degrees Fahrenheit, would be the area of maximum fusel oil concentration. I mention here also, which is the beginning of the third page of this, or the last page of this handout, that the temperatures in the fusel oil band are those which correspond to the so-called break. The operators used to talk about the temperature break. Well, the temperature break is simply that region in the column where the temperature changes very rapidly, and that's simply in the region of the boiling point composition diagram, where you're getting maximum change in concentration from very low alcohol up to very high alcohol, or relatively high alcohol, in just a few trays. And of course the temperature changes very markedly. If we plot the boiling point composition diagram again, without trying to be too precise here, shape something like that. And of course, the boiling point of water is 212 degrees Fahrenheit, or that is neglecting all pressure effects, and that of ethyl alcohol is about 174 Fahrenheit. And of course, at the down in the stripping section where you have very small steps here, because you're up in this corner here, while the temperature is going to read about the boiling point of water, maybe a fraction of a degree lower. In the middle point of the column, you get this maximum change here. So that if this was a temperature here, maybe 100 and what is this, 174, 185. Let's say this is maybe 182, something like that. The way I've drawn this, in effect, at equilibrium, you'd get this much change here in one tray. That'd be down to about maybe 176 here, just one ideal tray step. Now this, of course, doesn't take into account the reflux ratio. We have to revert to the XY diagram, the McCabe-Thiele type diagram, to take into account the reflux ratio. But anyway, it might be that much in one step. And so in this region of a column where the fusel oil decanter is going to be, let's say where you're trying to get about 130 proof, you're going to get, this might be 185 here, and the tray above might be only 177 or 78, something like that, and the tray below might read 195 or 192, something like that. I'm just guessing, but these are reasonable figures about what they'd be. So in other words, when you operate a column, there's a little bit of fluctuations taking place, and so when you're in a region here, frequently you can see the needle just clicking back and forth, not clicking, but flicking back and forth, because there's a temporary surges in the boil-up rate and a temporarily higher level on a tray of liquid than there is at a fractional interval later. And so you get a very rapid change you get a little change in temperature. Well, that's about where the fusel oil is going to be, or maybe slightly above it. So in other words, you need to have some temperature indicator in the region there, and there's much point in operating the decanter unless you have the temperatures in the right range. Third error, drawing the oils at an improper rate. In other words, there is a proper draw of rate that would be a reasonable rate. Depends upon the amount of feed or the amount of product being produced. I made a little example here of using a figure that about 0.2% of the alcohols will be the fusel oil. Now this varies, of course, with the type of mixture, but be as a ready rule. So I estimated here that on a balanced basis, a unit producing 500 gallons of high-proof spirits per hour, or wine spirits per hour, and considering that there's essentially no high alcohol in the wine spirit, that the fusel oil input would be about 1 gallon per hour, and then if your fusel oil cut is roughly 20% fusel oil, then it'd take about 5 gallons per hour to draw out to be in equilibrium, wouldn't it? To keep them to be in dynamic balance with the feed and the product removal. Since, however, a significant amount of the fusel oil is recycled back, well, I say that a reasonable figure might be twice that, or 10 gallons per hour. But there's no use in drawing 200 gallons per hour and expect to get a fusel oil decanter to work, because it just won't. It'll change the balance of your column. And then fourth point is what I've already referred to, using too much dilution water. I made a reference to some statement where you ought to use 4 to 8 volumes of water per volume of fusel oil, of low oils. Well, the evidence we've shown here indicates that something closer to 2 would be a more reasonable figure. And this reminds me of a little incident that I relate to. I was visiting a plant, I guess, again, it was in Lodi district one time when they asked me to come down and survey their distilling operations. And so one of the units is being operated to produce high-proof spirits. And it had a fusel oil decanter operating there with, you could see the water flowing and inside, looking inside the glass. And so as I walked by, I asked the operator or the manager, the winemaker, if it was working all right. He said, well, we never get any oil out. And I said, well, looks to me like you're running an awful lot of water in there. There's no flow meters, but just the visual appearance of churning of the liquid in there showed it was a pretty high water rate. And so I said, well, why don't we turn down this water valve to see what happens. So in the meantime, we walked on up the stairs and clear up to inspect the condensers. And lo and behold, when I came back down the fusel oil layer here, fusel oil decanter, here was a layer of fusel oil about 6 inches, 12 inches high up in the glass. And the winemaker looked at it, his eyes bugged out, and he confessed that it's the first time it ever produced any fusel oil since it's been operating. I don't know why he was operating it. And so the reason that the fusel oil suddenly appeared was maybe partly because of we were adding, as these graphs indicate, that we're adding so much water that was dissolving the fusel oil and running it back in through the water layer. As you see in these charts here, if you add a very high amount of water, while you the percent of isoamyl alcohol in the wash water. Well, I guess this didn't illustrate too well, but it would naturally go up because of certain solubility. But in reality, what the most important factor was in this particular incident I just related was the fact that this high rate of water and then be recycled back to the column was diluting the column. So in effect, you had a section of the column that was acting like an extractive distillation column, causing the fusel oils to go up high in the column, and probably also compounding your recovery of alcohol because there's an increasing amount of liquid that had to go out through the stripping section. So by cutting down on that on the water amount being added to the decanter, and therefore the amount being recycled back, the fusel oils then moved back down the column, back to where the thing was connected, so it began to separate. So you might check through those points again. I recommend that you have about 4 or 5 contiguous plates so that you can have a little choice, a little experience, but but particularly a temperature indicator on one more of these trays would be very useful. Then you should have flow meters to indicate the rate of the low oils draw and a flow meter to indicate the amount of water or some other indicator. And so you have a proper mixing ratio. And it would be another alternative type of a parameter that could be measured would be to measure the water or the proof of the ethyl alcohol phase, the wastewater phase leaving the decanter. And the rest of that last page here discusses a little bit about that. It should be something of the order of 16 to 20% alcohol would be a typical figure for the wastewater leaving the decanter, returning to the column. So with that, unless there's some questions, we'll conclude our discussion about fusel oil separation and decantation. Well, there was only one other aspect about distillation, and particularly practical considerations that I wanted to discuss with you briefly, and I won't have much time now today, but that had to do with disposal of heads, or the handling of the heads, or the aldehyde fraction. We've indicated many times that we take off a heads cut, either from the primary column, or maybe we have an aldehyde concentrating column, which we can concentrate the heads to a smaller volume and a higher concentration. Well, the question is, what are you going to do with it after you get it in the receiving tank? And this used to be a kind of a thorny problem with the operators here in the industry, because at least if you don't have a special aldehyde concentrating column, the concentration of aldehydes in this heads cut is likely to be, or really will be, as much as 1%. Impurities will be of the order of 1% or less. Even if you include ethyl acetate along with acetaldehyde and acetal as the impurities, it may be only 1%. As a matter of fact, the federal government, if the regulations are enforced in this respect, permits you to dispose of it and destroy it only if it has the amount of at least 0.5% aldehydes or more. At that level, it's considered to be a non-palatable or beverage, and so it can be destroyed. Similarly, fusel oil solution can be destroyed and disposed of if it has over 1% of fusel oil. I believe that figure is there. But nevertheless, going back to the heads, then you have a product here that's probably 190, 192 proof, and only 1% of it impurities. So you've got essentially 99% of the solvents in there is ethyl alcohol, which you don't want to waste. And so there was a lot of efforts in the industry 20 years ago to chemically treat the heads fraction in order to destroy the aldehydes in one method or another, and some of which have merit, but in practice are rather difficult. In other words, some of the chemical treatments that were used was treating with alkali. Well, if you have a solution of pure acetaldehyde and make it highly alkaline, the pH of about 10 or 11, the aldehydes do polymerize and can be somewhat removed by redistillation. But usually if you're distilling material that had been treated with alkali at a highly alkaline pH, you get some terrible odors that come out, some other impurities in there that give you amine-like stinky odors that will appear in the distillate, and so even though you might get rid of the aldehyde, you probably have a worse product than it started with. Another method was treat with oxidizing agents such as potassium permanganate and hydrogen peroxide. But in reality, under the conditions in which these oxidants were used, you actually sometimes produce more aldehydes by oxidizing ethanol than you're destroyed by oxidizing acetaldehyde to acetic acid or other compounds. Some of these methods might have been effective if they'd had good chemical control, but there was usually no analysis made of the amounts, no stoichiometric calculations of the amount of alkali or oxidizing agents to be added, and so there were a lot of chemicals wasted and without accomplishing much. Well, it's very well known that active alcoholic fermentation, the enzymes of yeast, is a very strong reducing medium. As recently as 1920, there was a little book put out by Hardin on alcoholic fermentation, and he summarized in there research reports which had indicated 75, as I remember, some 75 different aldehydes had been shown to be reduced by the reducing action of yeast during fermentation. So it seemed very simple to make a few tests and see if it wouldn't work, just to remove the aldehydes, acid aldehyde in particular, from heads. After all, the mechanism of alcoholic fermentation provides for the last step in the formation of ethanol is a reduction of acid aldehyde. And so it's as simple as that. To make a very long story short, that's the method that's used today.
Are you
And-
that tolerant of that high alcohol level?
Beg pardon?
Are you that tolerant of the high alcohol level?
Well, you have to add it, and I have some reprints here which give some recommendations on the amount that you can add. Now you can add yeast, you can add heads back to a tank of distilling material, or before fermentation or after, or at any stage in it. And the law provides that this is permitted as long as you're adding it to distilling material. You can't dispose of it in a fermentation tank that's producing wine, for example, for direct consumption. But there is some toxic effect of aldehydes and acetal to yeast growth. So we found out by experience and experiments that what you should do is add the heads to a fermenting medium after the growth phase is finished and at more or less the peak of fermentation. I'll put a set of these reprints in your reference reserve folder, but if you can just kind of see these two charts here, this indicates roughly the degrees Brix drop of a grape must as a function of time, and the left-hand side of the chart here shows various levels of pure acetaldehyde added to a certain medium. I forgot what I had to look up to see what it was. So increasing amounts of the acetaldehyde cause a delay in the growth phase. But finally, when the growth has overcome this toxic effect of acetaldehyde, well, then they go off at a rate which is parallel, and end up with essentially the same bricks here. But if you wait till the fermentation has decreased, I think the medium here initially was 15 bricks. Then when we added the acetaldehyde after vigorous fermentation, and the bricks had dropped to about 12, and adding various amounts of acetaldehyde from 0 up to 3.5 milliliters per liter, while the effect of the added acetaldehyde was minimal, even on rates of fermentation. They all ended up at about the same time of fermentation. So in other words, there's some practical rules, and one is to add heads to a actively fermenting distilling material medium after the fermentation is active, but not after it's gone too far, at about immediately after the growth phase is finished and active fermentation beginning. We have said that you should make an estimate so that you would not maybe exceed more than about 1% aldehyde added, as calculated as a percent of the volume of the medium to which you added. But most likely it would be determined by not adding too much to increase the ethyl alcohol content. We say that you should not add enough heads to increase the potential alcohol from the heads added plus the amount to be derived from the fermentation to exceed about 10% alcohol. So in practice, though, if you have a regular recycling of the heads back, even whether you're using low-strength heads directly from a column, or whether you're using high-strength concentrated heads from a concentrating column, the amount to be added back to distilling material has very small effect on the result, because it's a relatively small volume of heads in relation to the amount of distilling material you're normally producing. So that's all the time we got to talk about that this morning.